the rate of several centimeters a year as it degrades its orbit. And what we can see then is that if we have an insulating lid or a quench crust coupled with gravitational attraction and friction and heating, we can actually keep the magma ocean alive for longer than 200 million years. But remember, this is just a model. If we look at the Highlands Magnesium Suite, we can see here that we've got a lot of samples that have been dated by the samarium neodymium technique. They also form a range of ages, and you can see there that the uncertainties are also much different in some samples versus others. You can see that also that the Highlands Magnesium Suite, as typified by 76535, this has this equilibrated texture to it. It's a beautiful rock, but the texture suggests that something else has happened to this particular sample since it formed. Now, if we then combine our Pharonan Orthosite Suite and Highland Magnesium Suite samples with samarium neodymium ages, we have causes for concern. Number one, we have large uncertainties in several of these samples. Number two is that we have different ages for the same sample in a number of cases, both for the Pharonan orthosites and also the Highland Magnesium Suite. And maybe most importantly is that we have overlapping Pharonan orthosite and Highland Magnesium Suite ages. So the model that the Pharonan orthosite crust formed and the Highlands Magnesium Suite then intruded into it is now in question. If we then combine the Highlands Alkali Suite, you can see the zircon ages there also overlap with both the Pharonan orthosites and the Highland Magnesium Suite. And if the Highlands Alkali Suite is an evolved M member of the Highlands Magnesium Suite, they should be younger than those. So we should see an age progression, and we don't. So we have to go back and look at the rocks themselves. Getting an age date and doing chemistry on these samples is one thing, but how are the minerals related to each other, and what is the texture like? So what we have here are a number of Pharonan and orthosuite samples that have been age dated by the samarium neodymium technique. And what you see immediately, they have a very broken up texture, or what we term brecciated texture. This means that the impacts, meteoroid impacts that have been ongoing since these samples were formed have severely affected the texture of these rocks. Not only have they been mechanically brecciated, they could have been mechanically mixed with other lithologies, because we know from lunar reconnaissance orbiter images that impacts are still ongoing today. So this impact has to be taken into account, and how it's mixing these rocks. And yes, we may have a Pharonan and orthosite sample, but it may be made up of different Pharonan and orthosites of different ages, and that may be explaining some of the large uncertainties that we see in the samples, and maybe even the distinct ages that we see for some of these samples as well. For example, 60025. The Highlands Magnesium Suite samples are not faring any better either. 72215 is showing something that is undergoing equilibration. We're starting to see that interlocking texture that we see depicted very well by 76535, suggesting that they have been equilibrated and heated in the solid state, allowing this equilibrated texture to develop. Then we have 15445, where we see a very shocked material, where we can't see any defined crystal boundaries as such. They have been blurred due to the effect of this incredible shock through the meteoroid impact. Another issue comes from the data that's been gathered from orbit since Apollo. These are data from the Moon Mineralogy Mapper. This was flown on the Indian Chandrayaan-1 mission earlier this century. And what Carly Peters and co-authors have found from these data is that we have lithologies present in the lunar crust that we simply don't have any representation in our current sample suite. These are olivine, orthopyroxene or OPX, and spinel-rich lithologies, affectionately termed ooze by Carly Peters. Now, magnesium spinel is important because it represents another aluminous mineral. We've talked about plagioclase and we've talked about garnet. And now we're finding that we have magnesium spinel in the crust. So various models have been produced. This could be a direct product of the lunar magma ocean. However, it could also be an impact melt cumulate. You have a large impact, you get a lot of melt. It can also differentiate. Or it could be a reaction between magma and a plagioclase-rich wall rock that could also precipitate this mineral spinel. Now, the significance of these data is the fact that the pixel size from orbit is about 250 by 250 meters. And we're getting definitive signatures of spinel, orthoperoxene, and olivine over these areas. What we don't know is the geologic context of these. Have they been intruded into the crust? Are they a layered intrusion? We don't know. We need to do good old-fashioned geologic field work on the lunar surface at some of these sites to truly understand their origin and how they evolved. This would also include sampling. You could have very strategic sampling by an astronaut that would allow us, as we saw with 15415, that would allow us to get a much better insight into these new lithologies that we knew nothing about until the Chandrayaan-1 mission. Japan also had a mission, Kaguya, affectionately termed Selene, and what we see from the data that they produced is that they focused a lot on the crust. And we see that there is a dichotomy between the composition of the crust on the near side with that on the far side. We knew that there was a thickness dichotomy, as we see with the Mormari on the near side and less on the far side. But what we can now see through compositional evidence is that the Selene mission has showed us that the far side crust is more magnesium than the near side. And it may be the magnesian anorthosite rather than the Pharoan anorthosite is the dominant composition on that thicker crust on the far side. Now, this has implications of when plagioclase comes out of our magma ocean. We would have to have a much higher aluminium content in that magma ocean to affect that. But magnesium anorthosite means that it comes out much earlier in the sequence than does the Pharoan anorthosite that we've modeled using the Apollo data. So if we look then at the feldspathic highlands, we can see here are the Apollo data. But we've now got these lunar meteorites which contain an awful lot of highlands materials. They are representative of the crust in the area from which they were derived, but we just don't know which area they were derived from. We can assume far side, but where on the far side, we don't know. So if we then take these two fields, you can see here the Apollo magnesium suite and the Pharoan anorthosites, and we compare those with the data that have come from the feldspathic or highlands lunar meteorites, you can see that these are predominantly Pharoan anorthositic. However, they greatly expand that range of Pharoan anorthosites that we got from the snapshot from the Apollo samples. The problem here is that the Apollo samples have been affected by the Imbrium ejecta. They form a very narrow field that we now know is narrow because we can compare them with these feldspathic meteorites. So the lunar meteorites then are showing us that Apollo gave us a snapshot that was, again, not representative of what the rest of the moon actually is. So the models that have been developed during Apollo now have to be adjusted on the basis of new data. If we then look at what we did learn from Apollo, we can see that the differentiation mirrors that from the big intrusions that we have here on this planet. The ones that we have from the still water are not from a magma ocean. They are a large intrusion of magma. And you can see similarities in the trends there of the rock minerals in the rock types that come from still water with those from the Apollo samples. If we then compare that with the lunar meteorites, we see that the lunar meteorites show a much more greatly increased our understanding of the moon. We knew nothing really about the moon until we had these samples coming back. However, since then, we've now recognized that we have new samples in lunar meteorites. We've also had a lot of missions, there's a lot of international interest in our moon now, and a lot of international missions have gone to the moon, and the orbital data shows us that the models previously developed are somewhat lacking. They're being tested, and they need adjusting, or they need to be rethought altogether. We also know that while the meteorites are from the moon, we don't know where on the moon they're from. They're from unknown locations.